Good morning, everyone, and welcome. I'm pleased to have you here today. Today, we'll be exploring the fascinating world of pharmaceutical cleanroom design. Our focus will be on key considerations that ensure these environments are safe, compliant, and efficient. This presentation will cover essential aspects such as design principles, regulatory requirements, and best practices. So, let's dive in and discover what it takes to create effective pharmaceutical cleanrooms. Let's start by emphasizing that adhering to GMP cleanroom design principles is essential for ensuring product safety and quality. This means that every element, from airflow and filtration to zoning and material finishes, is carefully optimized to minimize contamination risks throughout manufacturing. GMP-compliant cleanrooms are not just built to meet standards, but also maintained consistently to support risk-based contamination control and to keep a stable control environment. Now, a key aspect of this is airflow control and understanding cleanroom air change rates. Proper airflow design forms the foundation of contamination prevention. It's critical that we supply, filter, and exhaust air at rates that are sufficient to dilute and remove particles generated by equipment, processes, or personnel. If airflow isn't properly managed, contaminants can accumulate, increasing the risk of product contamination. Moving on to air changes per hour, or ACH, this is a measure of how often the entire volume of air in the cleanroom is replaced each hour. Higher ISO classes, which require stricter cleanliness levels, demand more frequent air changes. This helps maintain low particle counts and allows for quick recovery times if contamination occurs, ensuring the environment stays within desired specifications. In pharmaceutical cleanroom design, understanding and implementing the right airflow and ACH rates is vital. It's all about creating a controlled environment where contamination risks are minimized, supporting both patient safety and regulatory compliance. So, in summary, proper airflow design and appropriate air change rates are fundamental to achieving and maintaining the clean conditions necessary for pharmaceutical manufacturing. Let's take a closer look at pharmaceutical cleanroom design considerations. When designing these environments, it's crucial to focus on several key factors. First, contamination control is paramount, ensuring that the cleanroom maintains the necessary cleanliness levels to prevent any product contamination. This involves selecting appropriate materials, controlling airflow, and implementing strict gowning procedures. Next, airflow patterns play a vital role. They help direct particles away from critical areas and maintain positive pressure to keep contaminants out. Proper HVAC systems are essential here, designed specifically for pharmaceutical applications. Additionally, ease of cleaning and maintenance can't be overlooked. The design should minimize crevices and hard-to-reach areas to facilitate thorough cleaning, which is vital for compliance and safety. Finally, regulatory compliance and validation are fundamental. The design must adhere to industry standards like GMP, and ongoing validation ensures the cleanroom continues to perform as intended. All these considerations tie back to our overall goal: creating a safe, sterile environment that supports high-quality pharmaceutical manufacturing. Let's talk about laminar, or unidirectional, flow first. This type of airflow delivers air in a straight, smooth path at a consistent velocity. Because of this, it minimizes turbulence, which is really important for keeping particles away from critical zones. You'll mainly see this in Grade A environments, where maintaining a very clean and controlled airflow is essential. The typical velocity for laminar flow is between 0.36 and 0.54 meters per second, ensuring a steady and uniform air movement. Now, contrast this with turbulent flow. Turbulent air mixes more within the room, which can be beneficial in lower-grade areas, like C or D environments. In these spaces, strict unidirectionality isn't as critical, so mixing air helps with temperature control and air distribution overall. It's also important to highlight that, to ensure these airflow patterns are working as intended, we often use airflow visualization studies, like smoke studies. These help verify that the airflow remains true to the design, which is crucial for maintaining the integrity of the environment. So, in summary, laminar flow provides a highly controlled, straight airflow suitable for critical environments, while turbulent flow, with its mixing properties, is more suited for less critical areas. Both play key roles depending on the environment's requirements. Let's talk about HEPA and ULPA filter classification and how we ensure their integrity. HEPA filters are designed to remove at least 99.97% of particles that are 0.3 micrometers or larger. These are the workhorses of cleanroom filtration, effectively capturing most airborne contaminants. ULPA filters go even further, removing at least 99.9995% of particles that are 0.12 micrometers or larger, making them essential in environments that require ultra-clean conditions. Now, for grade A and B zones, it's crucial to have 100% filter coverage. That means every part of the airflow system needs to be properly filtered, and regular integrity testing is a must. These tests use aerosol challenge methods like DOP or PAO, following standards set by ISO 14644-3 or N1822. This ensures that the filters are functioning correctly and maintaining the clean environment we need. Moving on to filter change frequency. This depends on a few key factors. Differential pressure readings can tell us when filters are getting clogged, while particle monitoring trends help us track actual contamination levels over time. Manufacturer recommendations also play a role here. Typically, HEPA filters are replaced every 1 to 3 years, but in some cases, as part of a preventive maintenance program, they might be changed more proactively. Finally, let's touch on filtration systems. In cleanroom ventilation, high-efficiency filters are used not just to control non-viable particles, like dust and skin flakes, but also viable organisms. These systems are designed to continuously maintain the cleanliness and safety of the environment, supporting the overall integrity of our controlled spaces. Now, let's talk about an essential element of cleanroom contamination control: maintaining proper pressure differentials between the classified zones. This is what we call the pressure cascade concept. The idea here is to keep positive pressure in the more critical areas, so contaminated air from less clean zones doesn't flow into them. You'll often see a hierarchy like grade A being the most critical, followed by grade B, then grade C, and finally grade D. The recommended pressure differential between these zones is generally at least 10 to 15 pascals. This helps create a controlled environment where airflow moves from the cleanest to the less clean areas, protecting the integrity of the critical zones. Now, shifting gears a bit to cleanroom zoning principles. This is about designing the layout in a way that supports efficient personnel and material flow, while still maintaining strict cleanliness boundaries. For example, you'll have airlocks for both personnel and materials to prevent contamination transfer. There should also be separate pathways for clean and dirty processes, ensuring cross-contamination is minimized. Another key point is the unidirectional flow of materials, which is crucial for maintaining the cleanliness standards. Just a quick note: improper zoning is a common finding during GMP inspections, so it's really important to validate your zoning during the design phase of your facility. Ensuring these principles are followed helps maintain the integrity of your cleanroom environment and supports overall contamination control. Let's talk about the importance of gowning procedures in cleanrooms. It's essential that gowning is performed in dedicated changing rooms that have clear zoning and step-over barriers. These barriers help separate the clean and unclean areas, minimizing contamination risks. When it comes to construction materials, they need to support easy cleaning and be resistant to chemicals. This way, we can maintain a sterile environment and prevent particle shedding. For example, wall panels should be non-porous, smooth, and flush, often coated with epoxy or PVC to ensure durability and cleanliness. The flooring must be seamless, anti-static, and resistant to chemicals. Materials like polyurethane floors are ideal. As for ceilings, in grade C or D areas, walkable panels are suitable, while in higher grade zones like A or B, sealed grid ceilings are preferred to maintain strict cleanliness standards. Furniture also plays a critical role. It should be made of stainless steel or powder-coated steel, both of which are easy to clean and non-shedding. Now, shifting focus to gowning requirements, it's important to remember that personnel are the biggest source of contamination in cleanrooms. Gowning protocols should be tailored to the specific cleanroom classification and aligned with the expectations set out in Annex 1. Proper gowning is crucial for protecting the environment and ensuring product integrity. Overall, selecting the right materials and gowning procedures helps us maintain the cleanliness and integrity of the pharmaceutical cleanroom environment. Ensuring the integrity of the filtration system is absolutely vital to prevent any contaminants from entering the cleanroom environment. This part of the qualification process is crucial because it directly impacts the overall cleanliness and sterility of the space. The filter system itself is designed to remove particles and contaminants from the air supply, but we need to verify that it's functioning properly. That's where the HEPA filter leak test comes into play. It involves checking whether the filters are correctly installed, free of leaks, and capable of effectively trapping particles. Performing this test is essential because any leaks could allow contaminants to bypass the filtration system, posing a risk to the manufacturing environment. A good tip here is to schedule regular checks on your filters. Routine inspections can help detect potential leaks early, before they become serious issues. Additionally, implementing a preventive maintenance program to replace filters as needed can help you avoid unexpected failures during critical manufacturing operations. Once your cleanroom is built and classified, it's important to conduct performance tests to verify that it functions within the specified parameters. These tests form the foundation for initial qualification, whether it's operational qualification or performance qualification, and they also support routine requalification, trending, and regulatory inspections. Monitoring non-viable particles with calibrated particle counters is a key part of this process. It helps ensure your cleanroom complies with ISO 14640-41 limits and supports ongoing environmental monitoring. Finally, testing the cleanroom's critical parameters, such as airflow, pressure differentials, and containment of contaminants, ensures everything is performing as designed. This comprehensive approach helps maintain the integrity and compliance of your cleanroom over time. Let's talk about the tools we use for airflow testing. For velocity measurements, we typically use hot wire anemometers or vane anemometers. These devices help us accurately gauge how fast the air is moving within the cleanroom. When it comes to volumetric flow rate, flow hoods or bolometers are our go-to tools. They allow us to determine the total volume of air passing through a point over a specific period. Now, focusing on the target specifications, for laminar or unidirectional flow zones, we're aiming for a velocity generally between 0.36 and 0.54 meters per second. This range helps ensure a steady, consistent airflow that effectively carries away contaminants. Additionally, the volumetric airflow needs to meet the calculated air changes per hour, or ACPH, as specified by ISO standards for the particular cleanroom class. Another critical point is that the velocity across the HEPA filter face should be quite uniform. A deviation of plus or minus 20% is acceptable, but ideally, we want as even a flow as possible to maintain consistent air quality. To achieve this, I recommend conducting airflow tests at different locations within the cleanroom. This helps verify that the airflow is evenly distributed throughout the space. It's also important to perform these tests in both at-rest conditions, when the room is not in use, and in operation, when manufacturing or critical activities are happening. This is especially relevant for areas classified as grades A through C, where maintaining strict airflow conditions is essential. Ultimately, understanding and verifying airflow characteristics is vital because they directly impact the air quality. Proper volume and velocity ensure that air is exchanged sufficiently and evenly, which is crucial for removing particles and contaminants. Maintaining this controlled airflow environment supports sterile manufacturing processes and overall cleanroom integrity. Maintaining pressure differentials between rooms of different cleanliness levels is crucial to prevent cross-contamination and to control the direction of airflow. When we have positive pressure in a critical zone, it acts as a barrier, preventing contaminants from entering those sensitive areas. Specifically, for critical zones like Grade A areas, it's important that they are positively pressurized compared to adjacent lower-grade areas. The recommended differential is usually between 10 to 15 pascals, or Pa, which helps ensure proper airflow direction. To monitor this effectively, pressure sensors or magnehelic gauges are used to provide real-time readings. These measurements are essential because deviations can indicate issues such as door leakage, filter blockage, fan failure, or incorrect damper settings. A helpful tip is to clearly define and document the desired pressure differentials between your cleanroom areas. This way, everyone knows the targets to maintain. I also recommend implementing real-time monitoring systems that can quickly detect any deviations, so you can address them promptly before they impact your environmental control. Finally, conducting an air pressure difference test regularly is a key part of maintaining a controlled environment. Consistent testing ensures that your pressure differentials are within the specified range, supporting the overall integrity of your cleanroom operation. Now, let's talk about laminar flow validation. It's essential that laminar zones demonstrate consistent, sweeping airflow without any backflow or dead zones. This is particularly critical in areas like aseptic filling, open vial handling, and media fill simulations, where maintaining airflow integrity helps prevent contamination. A useful tip here is to utilize airflow visualization studies. These studies can actively involve personnel, helping them understand and confirm that the airflow patterns are correct. Additionally, I recommend conducting periodic refresher training for cleanroom staff. Reinforcing the importance of maintaining proper airflow directions ensures everyone stays vigilant. Testing airflow direction is key. It confirms that the designed air movement patterns are maintained during operations. Visualization tools help verify that air flows away from critical product and component zones, which is vital for maintaining a sterile environment. Now, moving on to smoke studies, which are a powerful method for airflow visualization. By releasing non-toxic fog, like glycol or polyalpha-olefin-based fog, near filters, work surfaces, or potential turbulence points, we can observe how air moves in real time. These studies serve several purposes. They verify unidirectional airflow in Grade A areas, identify any turbulence or reverse flows, and demonstrate how critical zones are protected during personnel movements. Using smoke studies, we can see exactly how air behaves, ensuring that our airflow patterns are functioning as intended. This helps us confirm that the environment remains sterile and that the airflow is effectively directing contaminants away from critical zones. Overall, these visualization techniques are invaluable tools for validating and maintaining the integrity of our cleanroom airflow during everyday operations. Microbial contamination is a major concern when it comes to manufacturing sterile products. In this part of the qualification process, we focus on monitoring and controlling both airborne and surface microbial contamination to ensure safety and quality. We take air and surface samples regularly and analyze them to make sure microbial levels stay within acceptable limits. This step is crucial because it helps us maintain a sterile environment and prevents microorganisms from contaminating the products, which could compromise their safety and effectiveness. A key tip here is to establish a strong environmental monitoring program that provides continuous microbial surveillance. This way, we can detect any issues early and take action promptly. It's also important to investigate any deviations from microbial limits without delay. Corrective actions should be implemented quickly to address the root causes and prevent recurrence. By closely monitoring airborne and surface contamination and responding effectively to any issues, we help maintain the integrity of our sterile products and ensure they meet the highest quality standards. Temperature and relative humidity levels are absolutely critical environmental factors in cleanrooms. These tests are designed to assess whether the cleanroom is maintaining the specified temperature and humidity conditions necessary for optimal operation. Consistent control of these factors is essential because it helps ensure the stability of the products we're working with. It also plays a key role in preventing conditions that could promote microbial growth or compromise product quality. A good tip is to place temperature and humidity sensors strategically across the cleanroom. This way, you can capture any variations that might occur in different areas, giving you a more accurate picture of the environment. Additionally, it's important to ensure that HVAC systems are properly calibrated and maintained. Effective control of temperature and humidity depends on well-maintained systems, which help keep conditions within the specified limits. Overall, regular testing and careful monitoring of these factors help maintain a stable, controlled environment, crucial for quality and compliance in cleanroom operations. Now, let's talk about the recovery test and what it really measures. Essentially, it evaluates how quickly a cleanroom can return to its specified particle limits after a contamination event, like opening a door or personnel movement. These are common disruptions that can introduce particles into the environment, so understanding recovery times is crucial. When we refer to the cleanup period, we're talking about the amount of time it takes to bring airborne particle levels back down to the classification limits after adding a load, whether that's people, equipment, or other sources. In terms of benchmarks, for ISO 5 areas, the recovery time is usually less than a few minutes. That's pretty quick, reflecting the high level of control needed. For higher ISO classes, the recovery can be longer, and that's acceptable depending on how the HVAC system is designed. Here's a tip. It's really valuable to simulate potential disruptions during routine operations. This helps us assess how well the cleanroom can recover under real-world conditions, not just theoretical ones. And I recommend documenting and analyzing these recovery times carefully. By using this data, we can refine our protocols to minimize downtime and ensure the environment maintains its integrity efficiently. So, in summary, recovery time testing isn't just about measuring how long it takes. It's about understanding and improving our cleanroom's resilience and performance. When working with facilities that handle cytotoxic, allergenic, or highly potent compounds, it's crucial to perform containment leak tests. These tests help us ensure that air and particles stay confined within the designated zones, preventing any unintended exposure or contamination. The importance of these tests cannot be overstated. They protect both personnel and the environment by minimizing the risk of leaks. You'll often find these tests required in negative pressure rooms, isolators, and RABS, or restricted access barrier systems, which are designed to maintain strict containment. Typically, containment leak testing includes methods like smoke testing, where we visualize airflow and potential leaks, and filter integrity verification, which ensures that filters are functioning properly and can contain hazardous particles effectively. A good tip is to regularly review and update your containment systems. Technology advances, and lessons learned from past incidents can help improve safety measures. Staying proactive in this way keeps your containment strategies robust and reliable. And of course, thorough training for your team is essential. Ensuring everyone understands how to properly use and maintain the containment equipment goes a long way in minimizing leak risks. Proper training, regular reviews, and staying current with technological advances together form the backbone of effective containment management. Let's take a moment to look at how cleanroom classifications are aligned across different standards to ensure global harmonization and consistency. In GMP guidelines, you'll notice that the classification systems are often matched with international standards like ISO and US federal standards. This alignment helps streamline quality expectations worldwide and makes compliance clearer for everyone involved. Now, on this slide, we're comparing cleanroom classifications according to Annex 1 of the GMP, ISO standards, and US federal standards. The key point here is that, although the terminology and specific requirements might differ slightly, the overall approach is similar, focusing on controlling airborne particulates, microbial contamination, and particulate levels. By understanding how these standards correspond, we can better design and evaluate cleanrooms that meet multiple regulatory expectations. This comparison helps us see the bigger picture, that regardless of the standard, the goal remains the same, maintaining a controlled environment to ensure product safety and quality. So, keeping this alignment in mind is essential as we develop and validate our cleanroom environments, ensuring we're compliant internationally and supporting our overall quality management system. Qualification and validation are crucial steps in ensuring that a cleanroom consistently performs as intended. They help us demonstrate that the environment supports product quality and meets the strict requirements of GMP and ISO 14644-1. These activities provide us with documented evidence that, under defined conditions, the cleanroom can reliably meet its classification parameters. This includes both non-viable particle control and microbiological limits, which are vital for maintaining a sterile environment. It's important that our cleanroom validation protocols clearly define the sequence of qualification activities, such as design qualification, installation qualification, operational qualification, and performance qualification. These protocols must also be aligned with regulatory expectations and take into account specific contamination risks related to the product. By doing so, we ensure that the cleanroom not only meets standards, but is also tailored to the unique needs of our manufacturing process. This process helps us maintain a high level of control and confidence in our cleanroom environment, supporting overall quality and compliance. Let's take a closer look at the stages of cleanroom qualification. First, we have the design qualification, or DQ. This is where we verify that the cleanroom design actually meets all the necessary regulatory, functional, and process requirements. During this stage, we review layout drawings, zoning strategies, airflow directions, HVAC specifications, pressure differentials, and how materials and personnel will flow through the space. It's important to consider standards like Annex 1, ISO 14644, and specific contamination risks related to the products we'll be working with. This ensures the design is solid before moving forward. Next is the installation qualification, or IQ. Here, we confirm that every component installed, like HVAC systems, filters, sensors, and control panels, is done correctly and matches the design specifications. This includes verifying the placement and labeling of HEPA or ULPA filters, ensuring HVAC installation parameters are correct, and checking that construction materials, such as surfaces, panels, and flooring, are compliant with standards. Both these stages are crucial building blocks. They set the foundation for a reliable, compliant cleanroom that supports high-quality manufacturing and research. Now, let's talk about performance qualification, or PQ. This is conducted under in-operation conditions, meaning we test the cleanroom while it's actually in use, to confirm that it performs as expected during real manufacturing activities. Key aspects of PQ include microbial monitoring of both air and surfaces to ensure contamination control, as well as non-viable particle count testing to measure airborne particles that aren't alive, but could impact product quality. We also perform personnel and equipment challenge studies to verify that our processes are robust. Additionally, PQ is often linked to media fill validation in aseptic environments, which is crucial for ensuring sterility. We also use airflow visualization techniques, like smoke studies, to observe airflow patterns and confirm proper directional flow. Monitoring temperature and humidity is essential to maintain optimal conditions, and recovery time testing helps us understand how quickly the environment stabilizes after disturbances. When applicable, we check lighting and noise levels to ensure they meet operational standards. Moving on to operational qualification, or OQ, This involves testing all critical aspects outlined in ISO 14644 standards. This includes measuring airflow volume and velocity, and conducting aerosol challenge tests to verify filter integrity. Essentially, OQ tests the system's functionality under static, or at rest, conditions, ensuring everything operates correctly when the cleanroom isn't actively in use. Key OQ tests include verifying airflow volume and velocity, conducting HEPA filter leak tests to confirm filter integrity, and pressure differential mapping to ensure proper airflow paths. Together, these qualification stages, PQ and OQ, are vital for verifying that our cleanroom systems are performing reliably and according to regulatory standards, ultimately supporting the overall quality and safety of our manufacturing processes. Cleanroom classifications are absolutely vital in ensuring that pharmaceutical products remain safe, pure, and of the highest quality. It's important to understand the differences between GMP grades A through D and how they correspond to ISO 14644 standards. This knowledge helps us determine the appropriate environment for each stage of production, depending on the level of cleanliness required. Practical applications of these classifications involve tailored environmental controls and monitoring systems to maintain compliance. By aligning our practices with GMP expectations and establishing strong systems for cleanroom design, qualification, ongoing monitoring, and periodic auditing, we can create controlled environments that significantly minimize contamination risks. This, in turn, supports consistent product quality, which is at the core of our industry's commitment to patient safety. As technology advances and international standards become more harmonized, it's crucial to stay updated on evolving regulatory guidance, whether it's Annex 1, ISO 14644, or FDA recommendations. Adopting a proactive approach to cleanroom management not only prepares us for inspections, but also demonstrates our dedication to operational excellence and patient well-being. Ultimately, these efforts reinforce our role in delivering safe, effective medicines to those who need them most. For further support, please don't hesitate to contact us. We're here to help you with any questions or additional information you might need. Thank you so much for your time and attention today. I truly appreciate your engagement and interest. Remember, we're committed to supporting you beyond this presentation, so feel free to reach out whenever you need. Thank you again, and have a great day.